Okay, hi everyone. Next we have Harney Wang. He's talking about exact synthesis of quantum circuits in algebraic ZX calculus.
Okay, thank you for the introduction, Alex, and thank you for giving me the chance to present my work. Actually, this is an ongoing work, so I would like to thank Bian for useful discussions during my preparation. And so I will talk about the exact synthesis problem. So what is it? So that means given a unitary matrix, so decompose it into a quantum gate of a universal set. The exact synthesis problem is on how to decompose the unitary exactly. So the most frequently used universal set is a Clifford+T gate set. And the first algorithm for exact synthesis of single qubit unitaries in terms of the Clifford+T gate set was given by Kliuchnikov and Maslov and Moscow in the paper. And then later, Giles and Selinger proposed another proof for this synthesis method. And furthermore, they generalized this method of exact synthesis of single qubit Clifford+T unitaries and to the multi-qubit cases. But all of these results were based on the techniques from algebraic number theory. So my question is, can we do exact synthesis in ZX calculus? So I would like to try first for the single qubit case, which is because this is easy to get some ideas. And then once I know enough things about the single qubit cases, and then I can move to the multi-qubit cases. Okay, so first, let's look at the 2x2 matrices. So how do we represent these matrices in these diagrams? First, we use the map state duality to turn a matrix, 2x2 matrix into a 4-dimensional vector. And then by my recent paper, so I give a normal form for arbitrary vector. So this 2x2 matrix, when it is turned into a vector, and it can be represented by a normal form like this. So I would explain some components of the diagram later. And then what I want to do is to just simplify this normal form as simple as possible. And I don't want to to talk about details. And then let me just jump to the final simplification diagram. And then finally, you from the normal form, you get this one. And then you use the map state duality again, and then you got the representation of the 2x2 matrix like this. So where this we assume this A0, A1, and A2 is not 0, and the A green box is just the diagonal matrix, and the triangle is the elementary matrix, and the down triangle is just the transpose of this up triangle. And okay, so but this still not quite satisfying form. So we want to simplify that further. So how to do that? So first we have the two representations of a controlled phase shift gate. So which means a controlled ZR gate can be represented by triangles, or it can be represented by red and green nodes with phase angles. And this representation can be generalized to the arbitrary phases, complex phases in this form. So once we have this form, then we can rewrite this diagram into green and red nodes in this form. And also this one, for this one, we want to combine it into one single node. And so we introduce this new node, red box node, which is a conjugate to the green box by Hadamard. And so in this notation, so this diagram can be written in this green and red box nodes. And combined with the previous simplification, then arbitrary 2x2 matrix can be written in a square green and red boxes in this form. And this is a general matrix, so it's a kind of a generalized Euler decomposition. But if the matrix is unitary, and then for example, this paper, you can see that this unitary can be written in this form. And once we have this form of unitary, then we can substitute these values into the previous form, and then you can get exactly the Euler decomposition. That means we start from a normal form, and then we get the exact formula for the Euler decomposition. So because we want to represent any unitary matrix over this ring, Z O I and 1 over 2 root of 2. So we know that here in this ring, the U and V belongs to this ring, and the phase angle phi is a multiple of pi by 4. So you can see here, once the first column of U is determined, then the second column is almost determined, just up to a phase. And by this, by the algorithm, any such U can be decomposed into products of Clifford+T gates. So now, since we just obtained all exact Euler decomposition formula for the unitary, so now we just want to start from this Euler decomposition. How can we turn it into sequential composition of Clifford+T gates? So here the idea is, okay, so we want to start from this this Euler decomposition. We want to modify it step by step, iteratively, until it becomes a sequential composition of Clifford+T gates. And so first we need to decide what kind of gates we want to use to modify this U. And we basically have two kinds of gates. It's green phases and the red phases, right? And in they're all multiplied, the angles are multiple of pi by 4. But we can't just use the green phases because it will be absorbed. So we can't proceed. And also we can't just use the green phases and the red pi phases, because the red pi phases, it can commute with any other phases. So what should we do? So let's look at the permutation rule. That is a color permutation rule, so which is in a paper by me and Bob 2 years ago. So you can see from red, green, red, you can turn it into from green, red, green, you can turn it into red, red, green, red, and the opposite is the same. So, but the formula looks a little bit complicated. So we will use it in some condition. So with this permutation rule, we can do this kind of things to modify the unitary. So basically, we want to first we use multiple of pi by 4 green phases, and then red phases with also the multiple pi by 4. And to make them equal, you need to add the inverse. And then you can see you can fuse these two green phases. And now you have the red, green, red. And then you can use the permutation, color permutation rule, the P rule. And then you get, for these 3 nodes, you get, after permutation, you have the alpha 2, beta 2, and gamma 2. They are green, red, green. So, and then that's one modification. And then you can do many times. But the problem is, as you have seen, the permutation rule is quite complicated. So if the L1 is an odd integer, then the P rule is very hard to use. And we also don't want to these red nodes to be trivial, like to be pi or 0. So basically, so we just want to fix it to these nodes, red nodes, to be pi by 2. We just want to fix it to pi by 2. But since we have the Euler decomposition with the Harman gate, which has this form, then equivalently, that means we can use the green phase and the Harman gate. So now we want to use these two kinds of nodes to modify this U. So the first time we use the K1, and then we fuse them together, use Euler decomposition, and then you got the you got this green, you got this from green, red, red, green, red, and but this red pi by 2, which is very special. It's easy to calculate. Then you got the for these three nodes, you got R2, B2, and gamma2, and then you do the second modification, and you do it again and again. So then the next question is, where this procedure stop? So to analyze this, so we don't want to we want to look at it in a simple way, because we have set for a unitary, it can be determined basically by its first column. So that means we just plug a red dot here, which represent this vector 1, 0, and then you can do the above procedure, and then you got the to see what you will get for the first column. And similarly, you do this again and again. You can find there is a mode, a pattern. And so I will denote for each modification, you got beta 2, beta 3, and beta n, and so on. And so clear, you can see if beta n is 0 or pi, it's 0 or pi, and then you can then you will get this will be fused with the red nodes and then copied, and the angles doesn't matter, and then you will get stopped. The procedure will get stopped at 1, 0, or 0, 1. It depends on it is 0 or pi. So when it is beta n is 0, and then that means this sequence is just the times U is just this matrix, and because of this the left is unitary, and then it must be that this should be a unit vector. So that means this is a unit, and then that means you can return in this way. So you decompose U in this way, and also you need to decide these two angles, psi and phi. You can do it in two ways. And one is you compare the two the matches on both sides, or you can because here we just ignore the scalars, and you can, if you can put back the scalars, then you can trace the scalars, and maybe then you can get the psi and the phi. And similarly, if beta n is pi, and you can get a similar decomposition. So that's the basic idea for how to turn a unitary into a Clifford+T gate, and in so from the Euler decomposition. So the above procedure should stop at some step according to this algorithm, or to the normal form. And also by calculation, we have the following recursive relation, so which represent beta n from the by the previous betas and the gammas, and also for the gamma. And so naively, so how do we decide each ki? So we can just, because ki has finite 8 values, right? So we can try all the possible values to see if beta I is 0 or pi, beginning from beta 1. But this is naive because it scales exponentially. So as I said, it's an ongoing work. So the open question is how do you determine each ki efficiently? And also I think from the single qubit case work. So I think for the I have some very rough idea about the multi-qubit unitaries. So I think for these cases, you would like to use the diagrammatic representation of the cosine sine decomposition for multi-qubit unitaries. And this is described, this representation is described in Bob and Alex the book. And also there is a generalization of the PLU for the in discussed, I think, in Ross and others' paper. Yeah. So that's it. Thank you.
Okay, thanks, Harney. We'll again give a little bit of time for questions to come in on the Slack. In the meantime, I could ask you. So, where do you think the ZX calculus really comes into this? I mean, the P rule could be said as something that's really just about the Euler decomposition of unitaries. Do you think it's maybe in the multi-qubit case or something? It gets more ZX-y, or? Well,
I think first, I mean, the actually the P rule is not. The P rule is not Euler decomposition. At first, I give the formula for Euler decomposition, but the P rule is once you have the Euler decomposition, how do you change the color? So it gives you you need them to calculate the KIs, the values of KI, but not exactly use it because I have the recursive with the P rule. I have the recursive formula I have shown, right? Peter, this one. Yeah, that's I use it, and also the idea to from a ZX diagram. By the ZX diagram, you can have the idea on how to proceed.
Let's see. Okay. Peter M asks, are ZX diagrams the Feynman diagrams of quantum computing?
I think it's even more than a Feynman diagram, because the ZX diagram is, as you know, is not any intuitive. It's also a strict mathematical tool, right? So in this sense, I think it's even more than Feynman diagram. It's not just the denotation.
Even more. Okay, I guess if there are no further questions, you can head over to your own Slack channel and you might get a couple more questions there.
Okay.
But anyway, thanks again, Harney.
Thank you.